Ladies and gentlemen, welcome back to our first session with the topic name, Road Payments and Materials. My name is Taavi Tants and I'm moderating this session. I'm working in Estonian Road Administration in Road Development and the Investment Department as a Chief Engineer. We'll have 5 speakers today in this session before lunch time, so please keep in time limits. I'm very glad to introduce you first speaker, Professor Simon Hesp. He's a leader in the field of asphalt science of engineering in Canada. He has been since 1992 a faculty member in the Department of Chemistry at Queen's University in Kingston, with a broad research program on various aspects of asphalt material science and engineering. Nearly 150 students have worked in the Hesp research group over the last 25 years. He's going to talk about the improvements in asphalt cement specification and test methods. So the floor is yours, Professor Hesp.
Thank you very much. It's a great pleasure to be here again. This is my second visit to Estonia. I had never imagined I would ever be in Estonia, even once, but the hospitality is great last time, so I decided to come back and present some more of our work that we've been working on for the last, 15 to 20 years with the Ontario government. You are moving towards different specifications for asphalt, so it's important you learn from others what you shouldn't be doing and maybe what you should be doing. I have about 35 slides. We should go through it fairly quickly and maybe 1 or 2 questions at the end. So the main focus has been to develop better asphalt cement specifications. That work has been funded by a few companies, small amount of money, government, lots of money, and some municipalities as well that have struggled to get better roads. So the municipalities that I've worked with, Durham, Kingston, Peel, Timmins, York, and a few others, they have implemented some of the tests that I will be talking about. Big multinational companies, they provide additives and they sometimes want to push their products, but they've been fairly hands-off. I've always received some money, but no questions asked, no things that I would do. And the Ministry of Transportation, they've built many pavement trials for us, which we have used to learn things that we didn't know before. Natural Science and Engineering Research Council of Canada is the main funding agency for academic research. Without my students, I wouldn't be here. I wouldn't have been able to do any of this. I've been fortunate to get some of the best students from Queen's to work in my lab, and we've got great experiences for that. So in Ontario, we have experience with asphalt cement specifications, and it's been somewhat rough, to say the least. For the last 20 years, nearly 20 years, we've implemented the super pave specifications, developed in the United States in about 5 years' time in the 80s. Ontario was one of the lead states for implementation. So with a few 5 or 6 other US states, we were the first to implement, and it hasn't all gone smoothly. This graph here, it shows 2 pictures of a small part of Ontario. This is where I'm from, Kingston, Ontario. It's about 2.5 hours east of Toronto, and Montreal is over there. It's about same distance to Montreal. In red are the contracts that have failed prematurely. We implemented SuperPave in 1998, and about 2 years later, we started to see failures that were new to us. Within a year or 2, you see all sorts of transverse cracks everywhere, and that wasn't the intention of the SuperPave specification. So in 2003, the Ontario government agreed to build a pavement trial that I could design. They built 3 more after that, and I got samples from other pavement trials that were built in 1986 and 92, and 96 as well. So we have probably experience with about 50 full-scale test sections on different highways in Ontario and one in Alberta to better understand what causes low-temperature cracking. SuperPave, it stands for Superior Performing Pavements, I say, or not, probably not. It was developed in the 80s, fully implemented in 98 as AASHTO standard M320, and it encourages gel-type binders. If you gel your binder, you make more money. You can blow air through it, you can put acids in it, you can put waxes in your asphalt cement. It all increases your grade under the SuperPave specification, but it lowers your performance. But you can make more money. So there is an ethical and a moral question here. Well, for most companies, it's just about making more money, so that's what they've been doing very successfully. The other big issue that we have discovered in 2009, that is most of the asphalt cement in Ontario, about 50% of it, was tainted with REOB, recycled engine oil bottoms. That's what's left over when they recycle engine oil. Lots of it is produced, about 20,000 tons in Ontario alone on a yearly basis, and it all goes into the asphalt cement supply. So that wrecks about 500,000 tons of asphalt cement, and it's about half the supply in Ontario. Waxes, pitches, soaps, recycled asphalt pavement, recycled asphalt shingles, it all goes into the asphalt. And lo and behold, SuperPave rewards it. So that leads to best case to worst case performance in adjacent contracts. Sometimes we have 20 kilometers of road that doesn't show any cracks, right next to it another 20 kilometers of road that cracks in the first 2-3 winters. So that has been frustrating, difficult, and an arduous process to get improved specifications implemented, but we're getting there. Often when the road has cracked, people recover the asphalt cement, they test it under SuperPave, it still passes. Contractor says, well, it passes, you don't build your road thick enough. You have to build thicker roads. Or your staging was off. You paved too late in the season. You did this wrong, you did that wrong, but it is never the materials that is to blame. So we have developed test methods that accurately and repeatedly and with a very high success rate can show when it is the materials and when it is not. And 9 out of 10 times we find that there's something wrong with the asphalt cement. So this is SuperPave. I will not name this fellow, but someone dropped the ball. And it's easy to say, looking back, that someone dropped the ball because, of course, 20/20 hindsight. But then again, they had $150 million. They spent $5-6 million on the development of these asphalt binder tests. We have the cement. It's aged in the RTFO oven, aged in the pressure aging vessel. It's measured in a DSR and in the BBR. You get your XX, II, YY grade. So X is the high temperature grade, I is the intermediate, and Y is the high temperature grade. And this was all based on research that was published much earlier, so it was incremental. But it was a shift from penetration and ring and ball softening point to more expensive equipment. A rheometer costs anywhere from $40,000 to $100,000. A BBR costs about $45,000. So basically we got fancy equipment, new tests, acceptance criteria that nobody really understood where they came from, and that led to some problems. My philosophy is to ban what we can. We know they put in vegetable oil. We ask, well, you prove to us that that is a good thing. If we have bacteria eating our roads in a year or two and it falls apart, that's not a good thing. If we see that they put in pig manure, I say, are you crazy? But there's research being funded by the pig industry in the United States to look at pig manure in asphalt cement, believe it or not. So lots of other things that are less outrageous, but that are widely used are waxes as warm mix additives. Sounds good, doesn't it? Warm asphalt, environmentally friendly. In Ontario, we just lost a contract. It was 80,000 tons of hot mix on a freeway, 300,000 cars a day. It had warm mix additive in it. Only 1%, that's not a lot, it doesn't matter. Well, it does. 1% of wax is very bad for your low temperature cracking. So we basically, or I, not many people listen to me, but some that do, they take my advice and we ban what we can. When we know something is bad and it is in there, we ban it. And then we find new things, we know it's bad, we ban it. So the contractors and the suppliers, they just should prove to us that things are okay, and then they can use it. Because we don't always know what goes in, we also have developed the test methods, LS228, LS stands for Laboratory Standard, and it's published by the Ministry of Transportation in Ontario. It's a modified pressure aging vessel. Basic ideas were published much before SuperPave. LS299 is the double-edged notch tension test, modified ductility method, first developed in 1903 by Alan Dow in the Washington, D.C. Roads Department. And then we have the extended BBR test, which is the modification of the regular BBR. And it was discussed during SuperPave, was also discussed by Alan Dow in 1903. So nothing really new, but a heck of a lot improved over what the regular AASHTO M320 specification does for you. The big issue that I mentioned already is the presence of REOB, recycled engine oil bottoms in asphalt cement. 50% in Ontario, up to 20% by weight. 30% of all the asphalt cement sold in the US tests positive for zinc and molybdenum. The zinc shows up in the X-ray fluorescence here. This peak, or the two peaks here at 8.6 kiloelectron volts, that's the signal for zinc. And we find copper, molybdenum, lead, arsenic, whatever is in your engine and the kitchen sink, we find it in the asphalt cement. This sample was offered to the Ministry of Transportation in Ontario. It grades as a -40 asphalt cement, PG -40. We estimate from the zinc peak that it had about 35 to 40% of REOB in it. So we're no longer talking about asphalt cement, we're talking about non-stick asphalt. It meets the asphalt AASHTO M320 specification for -40 grade, 58 -40, Northern Ontario. Don't ever use this in any road because it will fail before the winter probably. And the zinc compound that we find in the recycled motor oil, that's an anti-wear additive for your engine. So that's how we discovered everywhere we find REOB. I don't think you have it here yet, but it may well be coming. It's being banned all over the US and in Canada. They may ship it to Estonia or Russia or what, you don't know. You don't want to know, you want to be prepared. You want to make sure they don't ever put this in your asphalt cement. Why? This is two images from a test road we have about 10 hours north from Toronto. They're identical PG grades, -34 to 36. This is the trial I designed in 2003. We have 7 test sections. I'll talk about it a bit more in a minute. On the left, we have section 1. These are pictures at 8 years of age. It's now 14 years old. It's still in the same shape. Virtually no distress, just some core holes with some cracks through it. On the right, at 8 years of age, we had a section which has SBS polymer and some motor oil added to it. They don't mix very well with asphalt cement, so it phase separates, you get moisture damage, you get low temperature cracking, you get block cracking, you get fatigue cracking, you get potholes, you get everything for free. Well, it doesn't cost too much for the supplier to put it in and make a lot of money because it sells for $100 a ton, REOB. Asphalt cement was selling for $600–700 a ton. You do the math, they put in 10–20%. They make an extra 40, 50, 60, 70, 80 bucks a ton profit, and the taxpayers are on the hook for early repairs. So this section now has lots of potholes. This is all opening up, and it has to be replaced probably at 15 years of age, and it's beyond repair, and it's a hopeless situation. On the right is the kind of performance we see most of the time. On the left is something that is very rare now. We have a few contracts in Ontario that are better or similar in performance, but most of them have a life cycle that is reduced by maybe 10 years from what it used to be prior to Superpave. Ontario government is looking at performance warranties, 7-year performances. You look at the road, no cracking, everything is fine, the contractor is off the hook. Any distress, they have to repair or replace. So this is one trial contract on Highway 118. I visited it. I chip a little piece of the shoulder, nobody is looking, and I tested it in my lab, X-ray fluorescence, we found motor oil. So the contractor bought the asphalt cement from the supplier, and he signed a warranty, 7-year performance. Well, this is at age 5. You can see the road is cracked completely, and this could be a death sentence for a medium-sized company. If they have to replace that at age 7, then they could go belly up. So there's huge issues and huge problems with the asphalt cement supply, the quality, the purity, and so on. So besides banning everything, that's just legal language in a contract, we develop test methods. I'm a scientist, I'm an engineer, and we have worked for a very long time, maybe for nothing, on the development of the extended BBR test, which is simply a modification of the regular BBR, and it cools your sample for 3 days instead of 1 hour. You measure the creep stiffness and the M value, which is the relaxation rate, at 3 days rather than 1 hour. You do it at 24 hours as well, just to get another data point. Lo and behold, after 3 days, all the good stuff passes and the bad stuff fails. We get almost 100% success rate to sort out what has air-blown asphalt, motor oil modified, waxes, it all fails. And the good stuff, with the good quality crude oil asphalt, it still passes. So it's a very successful method. It measures the physical hardening tendency when you store a sample at low temperature, and for 3 days you lose your grade, or not. We now have samples that don't lose any grade. Good quality naphthenic crudes produce good quality asphalts. And this was discussed in the literature, well, this Dow fellow in 1903, he discussed it. They hardly had any asphalt pavements in 1903, but he was already talking about physical hardening. And in 1936-37, there was a guy in the States, Traxler, who did most of the work in this area. Not much is new today. So AASHTO has adopted this as a provisional standard, pushed by MTO, the Ministry in Ontario. They went to AASHTO and they adopted it as a provisional standard. Nobody in the US is using it, but the New England states are looking at it. Tremendous amount of opposition from industry because it cuts out waxes, air-blown asphalt, REOB, and a whole bunch of other things that they like to use. So these are the cracking data for the trial in Timmins. You can see on the left in red, minus 34 to 36 grade, 7 test sections. Accuracy, 0. There's no correlation between cracking and performance grade. So that's your AASHTO implementation. You got it there. If that's what you want, then you can have it. But I would say you're making a mistake. In yellow is the recovered asphalt cement. And you can see here, this point of section 4 is about a 10 degrees error. At 1 hour, it's about 10 degrees warmer grade than what the PAV residue suggested it should be at 8 years. So the PAV has a problem. We know that, and we have addressed it with LS228, which is the modified PAV. The other interesting thing is that this test section here it grades perfectly at minus 34 or a bit less, minus 33.5 or so. So at 8 years, the PAV has worked fairly well for that because it was started off as a minus 36 and it's now only a minus 34, no cracking, that's what we want. So for good asphalt cement, SuperPave works fairly well. You cool for 3 days, it becomes a minus 29. So the LTPP bind software shows for Timmins, Ontario, we need a minus 38. But even with an extended BBR grade of minus 29, we have no cracking for 14 years. So obviously that suggests that the BBR is not measuring exactly what we would want. We have implemented the extended BBR in a municipality. This is one of them to the west of Toronto. You can see in yellow we can catch borderline performance. And these are contractors that are pushing the limits. They want to make some extra money. They may be putting in some cheaper asphalt cement, or they may be adding some RAP when there shouldn't be any RAP. Municipal staff wants to enter the plant. They say, okay, we can't come in, health and safety. Please come back another time. We give you a can of asphalt, this is what we're using. But they may well be adding RAP when no one is looking. This is another municipality, and we have 3 samples that are no longer minor borderline. Well, one is, the other 2 are failures. What should be a minus 28 is a minus 25, that's a big problem. Or a minus 23, that's a disaster. This municipality had about 10 contracts crack in the first winter before the warranty started, in 2014 and 2015. So they've implemented now acceptance based on a recovered AC. And it works. This is production, this is quality assurance testing done in my lab. And you can see most of them passed. They were all notified. We are testing the recovered AC. But the contract still said it was based acceptance on the tank samples, which we have now changed to the recovered AC. So they will never do this again, or they will pay for it. This is what you see when you have an error of 6 degrees. You go from 98% confidence to about 50% confidence. And your chances of no damage in a given year decline from about 100% at year 0 to about 0% after 5 or 6 years. That's with an error of only 5 or 6 degrees. And it's just weather statistics. There's more problems with thermal stresses being way too high, but won't go into that. So before I go on, we talk a little bit about work of others. There's pictures in the literature from Löber et al. They're French from ExxonMobil. Mobil it was at the time, there was no merger yet. They did the first AFM studies on asphalt binder, and they did some SEM studies as well at the bottom on the left. This is SEM and this is AFM. And this was really shown 50 years earlier with optical microscopy, that asphalt cement has a structure to it. Then in 2002, you had 2 researchers from Eastman Kodak. They did more AFM, and they showed these ripples that they called the B structure. Someone did. I don't know if it was Löber or the others or someone else. And today we have beautiful color photographs that show the wax crystals, these white and black zebra patterns, B structures, and they phase separate, they precipitate out, and then they attract more saturates. So you get a phase separation that looks very much like this, although there's a different scale there. So that's what happens at low temperature. You put your asphalt cement at low temperature, it physically hardens. We have done a theoretical analysis according to Ozawa, and it measures crystallinity versus the cooling rate. When you cool it slowly, the grade is lost. When you cool it fast, like the regular BBR test, you get a very good grade, but it doesn't mean too much. So this Ozawa constant, N, the higher it is, the faster it hardens. So that's what we've been measuring, crystalline fraction in N, and we have seen that if you have a higher crystalline fraction, it physically hardens faster. It's air-blown, it physically hardens faster. So basically it's a sigmoidal rate equation, slow at first, then it speeds up, and then it depletes, there's no more material to crystallize, and we get the structure that forms. And this is another ESEM picture, environmental scanning electron microscope, and you can see that this is what consolidates in time. It takes time, it takes 3 days to form this structure at very low temperatures. Modulated DSC, differential scanning calorimetry, we can measure the crystalline fractions by that area under the dotted line. We measure the heat flow in a little pan, and we measure how much waxes melt. So on the left, section 1, we can see it has a crystalline fraction of 0.36%. On the right, we have section 4, it is 1.06%, quite a bit higher. And therefore, it hardens faster. So this is the analysis according to the Ozawa theory, very high correlation, R² typically 0.9 or better. And we can see the slope, which is the Ozawa exponent, for section 4 is much higher. And that slope gives you the rate of physical hardening, so that relates to the cracking performance. The ARAN data, automatic road analyzer data, automatic crack detection, we found in 2014, section 1 at about 168 meters of cracks, but lots of it through core holes. And section 4 about 2,000 plus meters of cracks. So it's about a 13 plus fold difference. That's huge, best to worst case performance in adjacent test sections. Identical design, identical climate, identical traffic. So if you look at the Ozawa analysis for the PAV residue, it's better than the regular grading. If you look at the recovered asphalt, it's almost the same as the ARAN ratios of the cracking. So physical hardening can explain the differences in performance for all these test sections fairly well. The key problem is the PAV is done on a tank sample. The recovered asphalt after 10 years, you cannot get it at production because you have to wait for 10 years. So the key is, what do we test at day 1 to predict the performance at 10 years? So we have to modify the PAV, we have to modify the rheological measures that we do. The other test I briefly discussed is the dent in the modified PAV. So the dent test is double-edged notch tension. We measure a CTOD, which is a critical crack tip opening displacement, and it's how far we can pull a hair of asphalt cement apart before it fails. On the left, it's brittle to ductile. On the right, it is ductile, and on the far right, we have polymer modified. So they fail in very different ways. We don't really care how it looks. We only care how far can we pull it before it fails. Like a ductility test, but this is a more fundamental mechanistic ductility test than what we have from Dow in 1903. The CTOD is reduced by lower temperatures, stiffer binders, waxes, acids, air blowing, recycled asphalt, pitches, REOB, and the blending of incompatible binders. So it does the job, what we want it to do. It sorts out the good from the not so good asphalt cement. And it increases by higher temperatures, softer binders, and some polymers, but not many polymers, and not more polymer is better. We have validated it at Federal Highways Administration, at the Turner Fairbank Highway Research Center, and the CTOD came out on top in both the lab and on the ALF lanes that they tested. It showed the highest correlation with the cracking distress. But we have validated it many, many more times in Ontario with real-life pavements, and it always seems to correlate fairly well with cracking severity. So it's now implemented across Ontario. AASHTO has also accepted this as a provisional standard, and basically nobody in the US is interested in it. And that's because they have their own test methods and they want to continue to modify the superpave, and they will never go back to anything that looks like a ductility test, and it's not made in the USA. So we have a little bit to go, but the New England states are looking at this. They're interested in it. Finally, LS228 is the modified PAV. If you age your asphalt binders for longer in thinner films, or in even thinner films, dry or wet, you can reduce the error in your grade determination compared to what it is after 8 years in surface quite dramatically. For the regular AASHTO grade, the error is about 6.2 degrees on average, ranging from a few degrees to 12 degrees, which is too much. But you age them longer at low temperatures in LS308, the extended BBR, or in the PAV, you get better performance or better match between your grading and your recovered asphalt cement. So at 25 grams, you can reduce the physical hardening as well. And a final slide, I'm running out of time, but the final slide here relates the phase angle temperature with what we get in the BBR on the left. And you can see this is 30 degrees phase angle, 45 and 60. At 30 degrees, there is some correlation, but it is not very good. On the right, the same phase angle temperatures are correlated with the extended BBR. And you can see at 60 degrees, it's not very good. 45, it's okay. But at 30 degrees, the phase angle correlates highly with the extended BBR test results. And this is one of the most important slides of my career, probably, for the last 15 years. We got the data this year. It shows that the BBR has a serious problem. Extended BBR, we know it works, it's very good, but it takes 72 hours to cool your asphalt cement samples. The phase angle is measured at warmer temperatures, and it takes 15 minutes of conditioning. It's much more convenient, it can be done like that. So that means if you want to spend money on a DSR and a BBR, then forget about the BBR. You can probably do it with the DSR, but there's some research to continue on that. Finally, I want to show a video. It is 1 minute or less, or half a minute, and this shows just two adjacent contracts. If you can start it for me, that would be great. This is one that is 10 years old. It has about 4,000 cars a day. And it is pretty good performance. There is virtually no distress. There's maybe one transverse crack if you look carefully. It's a good quality asphalt from Alberta, and there's no motor oil for sure. The same design, the same road, adjacent to it. This is 12 years old, and this has a little bit of motor oil problem. It was sealed for 66 kilometers of cracks within the first 5 years. But as you can see, the sealing didn't help too much because it's cracking in between. So this is only 2 years older, it's 12 years old. So this will last about 15 years, and then they have to replace the whole road. It's hopeless, it's a disaster. In conclusion, the under-design of cold temperatures remains to be a serious problem, as it has been over the last 100 years. EBBR and DENT do a better job. They're implemented because they give a much improved grading. The PAV still needs to be improved. We're working on that. We've done it with LS228, but again, there can be further improvements. And then it is imperative to test the recovered asphalt cement, because you can test the tank sample from the plant, the contractor gives it to you, and you could be wasting your time because there's wrap issues at the plant, or they add a different asphalt cement on the mix. So take loose mix samples from the paver, recover, extract the asphalt cement, and test that. You can save a lot of money as an agency. So I wish to thank you, and if there's any time, one question. If there's no time, you can always talk to me in the hallway, and at lunch, I'd be more than happy to answer any questions there. Thank you.
Thank you, Professor Esp. Does anybody has a question for Professor Esp? No. But I'd like to ask, what kind of residues do you recommend to use? There are a lot of forbidden, what are not good for bitumen. They seem to be for environment good, but not for bitumen.
The basic philosophy of superpave is correct. You need to use the right grade for the climate that you experience, plus or minus a few degrees. But you need to look at the durability also. So if you have a minus 34, it should stay as a minus 34, as we saw in the test section. So you have access to good quality asphalt cement, but you're probably also exposed to not so good quality asphalt cement. So the key is to test and then use the right grade for the right application. If you have a busy road in Tallinn, 50,000 cars a day, then you may skimp a little bit on the low temperature end if you want rut resistance, yeah? But even there you can do well. We have Trans-Canada Highway test sections. We have test sections right in Toronto with 300,000 cars a day on the highway. And they don't show much distress if you choose to low temperature grade correctly. The key problem is now it's a shot in the dark, so that's the issue.
Thank you again, Professor Esp.
Thank you.
Now, our next speaker is Mr. Audrus Vaikus. Audrus is a director of a Road Research Institute of Vilnius, Gediminas Technical University in Lithuania. He's going to talk about low-volume gravel roads analysis in Lithuania. So, the floor is yours.
Thank you, Tavi. Dear participants of this great event, Baltic Road Conference in Tallinn, today I would like to talk about gravel roads, and before the presentation I would like to present my colleagues of this research project, which we are doing quite a long time. And so the colleagues are Viktoras Vorobyovas and Dovidijus Šernas from the same institution, Vilnius Gediminas Technical University Road Research Institute, and also our colleagues from next biggest town in Lithuania, Kaunas, Algirdas Pakalnis and Aivaras Vilkelis from Transport and Road Research Institute. So today I will talk about gravel road situation in Lithuanian road network, and you will see that we still have a lot of those roads in Lithuania. And outline of presentation would be that we have to solve quite difficult problems regarding gravel roads and environmental facts. And shortly, objective and selection of the test sites, how we perform it and how we decided which site should be tested. And research results which are divided in two parts. First is about visual inspection, and the second one about the pavement structure and materials. So summary and some recommendations for improvement and general conclusions in the end. Here you can see that Lithuanian road network consists of almost more than 21,000 kilometers, and it's excluded municipality roads. It's only national roads of national significance. And till now we still have 33% of gravel roads in our national network. So, and this leads to a lot of problems, starting from low driving comfort, high costs of maintenance and vehicle amortization, fuel, and also environmental impact for society, for humans, and also for animals and etc. Here we can see the graph of gravel roads distribution decrease of gravel roads in Lithuanian road network. And you can see that starting in 2006, we started the gravel roads asphalt program, and through 5 years we reached quite reasonable numbers of decrease of gravel roads, but afterwards we stopped, and it was almost the same situation through the 5-6 years. And now, starting from 2007, you can see that we are willing to decrease number of gravel roads. And I can say that it seems that it will be achieved, and starting from 2016, and this year it will be paved a lot of gravel roads in Lithuania. So what I would like to state here that seeking accurate budget planning and smooth construction procedures, we have to know what we have, and do we have to excavate all materials from gravel roads, or still we can use some of them. And this research project was allocated to that. So main tasks of research are presented on this slide, and in the beginning, visual assessment and visual evaluation is very important to collect the distresses of a pavement, width of a pavement, and other things. And afterwards, we have to think about pavement structure, because after rehabilitation, we want to come back to this road not earlier than 20 years. So, project schematic. The project, actually, it is two projects, and first stage of the project started in 2013 and ended in 2014. And you can see that it was all gravel roads which traffic flow was more than 200 per day. So we selected all the gravel roads which were traffic flow was more than 200 per day. And actually, in 2016, the second stage of the project were started. And you can see that through the 2 years, from 2014 till 2016, we got new sections with the traffic flow which is more than 200. So 186 new sections with such traffic flow. So that means that traffic flow increase every year, and even in low volume roads it's increased. In general, in the first stage we tested 1,425 kilometers in length with gravel roads, and second stage is even bigger one, it's almost 3,000 kilometers. And today I will present information only from first stage of the research. So where is a methodology for visual inspection? And we have 6 characteristic groups, and also different severity levels. According to these severity levels, we collect and combine these numbers, and we get the general result of each road section. So here you can see some real pictures from roads and some distresses and severity levels. So here you can see some small rutting, bigger ones, and local rutting, not in all road, but only in some sections. Ruts and water in those ruts, and it could be said that it is combined distress, rutting, and also related to road width. Here we can see low severity corrugation, medium severity corrugation, and high severity corrugation. Of course, corrugation, we can say that it is very much dependent on maintenance level, and one day it could be very much corrugated, and after some activities which should be done annually or even few times per summer period, we can get another result. So this corrugation distress are a little bit tricky one. Some potholes or even displacement of the structure. Potholes in curves or intersections. And potholes related to profile issues. Slopes of embankment. We can see also that we have different situations and different problems. And also culverts were investigated, and we can see that in a lot of them, we have water. You cannot see here, but it is half of culvert is under the water, and it is not after the rainy period. So ditches, and even some ditches after rehabilitation or maintenance procedure. So we did collected all results and made a map for Lithuania districts, and you can see that. Maybe I will go a little bit further. So overall condition of tested gravel roads, and we can see that quite different situation is dependent on the region of Lithuania. And we can see that satisfactory situation with the level of not more than 30 grade is only in 2 regions. So in other regions we have a lot of problems with gravel roads, and we have to recalculate. Do we want to maintain gravel roads, or we have to be a little bit more faster and to go to paved roads and to save money? The second stage about payment structure. We can see the typical payment structure. Here it is presented, what we usually use for new gravel roads, which actually we do not build new gravel roads. But still the gravel road payment structure should comply with this regulation, and we have wearing layer of not less than 5 centimeters with special particle distribution and not less than 15% of fines in that. Then we have 15 centimeters of unbound base layer and not less than 25 centimeters of sandy layer for frost resistance. And here you can see test methods which were performed in the lab with materials took from the roads. And on the right, you can see the variety, some samples of the payment structure, real payment structure in road sections, which were tested. And I forget to say that we tested not less than 1 sample per kilometer in that project. So we can see a lot of differences in payment structure thickness, layers, materials, and particle distribution. Here is some photos from extraction procedure, and you can see that different type of materials are in the pavement, and actually you can see that there is no wearing layer of 5 centimeters or thicker one, and we have quite big particles in the wearing layer, so it's not good for maintenance of the gravel road. And results of gravel pavement structure, it can be stated that thickness of pavement structures and composition is dissimilar in the same test section. So if we test, for example, road section for about 4 kilometers, so even in that short distance, the pavement structure was dissimilar. And in 68% of all test sites, the thickness of pavement structure is less than nominal, so it's less than 55 centimeters. And almost in all cases, particle size distribution do not comply the requirements for wearing layer. But it can be stated that 23% of situations were satisfactory when we talk about base layer and base layer particle size distribution. But when we come back to frost resistant layer, we get the results that in 83% situation, we do not get right permeability of the material of that layer. So it's also we have to think about situation. If we want to use the same material, we have to think about permeability of the pavement structure for water. And some additional information which I wanted to include to this presentation. We have had 6 small sections in which we perform following weight deflectometer measurements for bearing capacity, to measure the bearing capacity and the actual differences in summer period and spring thaw period. And you can see that differences between E-modules of wall pavement structure, summer and spring, vary from 1.58 to 4.09. So actually we have very weak road sections, gravel road sections, then we have, for example, the lowest value of E-modules 40 on the top of the gravel road. So it's not compatible with the traffic which is using that road. Another thing, we try to calculate how many we lose during the use of that road, and we can see that it very much dependent on the traffic flow. And if we take, for example, more than 300 vehicles per day, we can lose about a little bit more than 1 centimeter per year. You can see that from 55 to 45 per 10 years. Materials in dust procedure and intermixing of materials, it is lost. So summary of condition improvement. We presented 4 variants, and it include some decision with keeping the same situation but adding some materials, also repaving, and all 4 variants were calculated how many it could cost, or it will cost, and it was presented to Lithuanian Road Administration, and according these variants now we perform paving program for gravel roads. And general conclusions. So, as it was said before, actually there is no such road sections in which everything is okay. So we have no such sections, or this percentage is very low. And actually 10% of tested sections can be used as base layer or base structure for asphalt concrete road. So 10% we can save, not less than 10% can be used. And it's stated that 90% should be excavated, but afterwards we say that if we will use some special techniques, we can save more, and we can keep the material on the road using, for example, soft asphalt or double auto seal, which we're doing from 2012, and it performs very well. We can save more existing pavement structure in gravel roads. So, and one conclusion about visual inspection, that 12% of gravel roads are in good condition and 32% in satisfactory. And more than half of surveyed gravel roads are in bad condition. So it also was presented in the map of Lithuania that more than 50% of the roads are in bad condition. So it should be the signal for the government, for the road administration decision makers, that we have to be more fast and more precise. So thank you very much. And if you have any questions.
Thank you, Audrus. If you have questions, then please. No questions. You're lucky. You can move on, and to save our time for lunch. Thank you. Our third speaker is Mr. Artūrs Riekstins. He's a road engineer at Latvian State Roads. He's going to talk about very thin asphalt pavement overlays. So the floor is yours, Artus.
Hello everyone. As you heard, my name is Artūrs Rēkstiņš. I'm from Latvian State Roads, and today I will tell you about research on restoration and reconstruction technologies of asphalt concrete for very thin layers. This research was created by cooperation between Latvian State Roads and Riga Technical University. Head of research, Viktors Haritovs, researchers Artūrs Rēkstiņš and Jānis Tihanovs. Aim was to develop asphalt concrete mixes for very thin layers with high performance properties by using traditional Latvian aggregates. Main tasks was research on renewable technologies for bituminous pavements like slurry seal, chip seal, microsurfacing, and asphalt concrete for very thin layers, or in other words, BBTM. Testing of raw materials and their comparison with existing specifications, design and preparation of mixes, and testing of performance properties. For example, wheel tracking test and shear resistance detection. It's very important to follow this popular sentence, right road, right treatment, right time. It will save you all kinds of resources, like money, time, workforce. There are also countries where road conditions are rated from 1 to 100. And in this case, there is opportunity to effectively plan a budget and timely restoration. Every year restoring this value. And in this picture, you can see recommendations. If, for example, if a pavement condition index is 80, then you should use single microsurfacing or double microsurfacing. We research various pavement distresses, and it's very important to understand how pavement distresses evolves. And there are two groups of them. At the surface deformation belongs fatigue cracking, block cracking, longitudinal cracking, transverse cracking, and showing. The next group is surface defects. It's rotting, bleeding, polished aggregate, and raveling. This image shows other renewal methods which are widely used in the world. And there is three groups of them. At the first group, surface dressing, it includes fog seal, rejuvenators, and chip seal. Second group, it's called emulsified mixes with fine aggregates, and it includes slurry seal and microsurfacing. And the last group, hot asphalt concrete, it includes traditional overlays and thin overlays, or in other words, BBTM. And now more about thin overlays. Advantages: lower costs, good surface properties, noise reduction, good water runoff, quick laying, milling is always not necessary, may improve the evenness, no modification to asphalt plant, and of course smaller labor input required. Disadvantages may be laid in good weather because thin layer cools fast. Manual paving is not possible in good quality, of course, and aggregate quality must be high. And the last one, noise reduction decrease over time. So in this picture, there's recommendations. For example, if you have block cracking, then you have to treat cracks, fill them with mastic, and then you can use thin overlay. But on the other hand, if you have, of course, structural deficiency, then it's not recommended to use thin overlay. This table is informative. Here you can see tips when to use each of the recovery methods. For example, thin overlay is recommended if you have a problem with roughness, limited rutting, and cracking, but not recommended if there is flashing, bleeding, raveling wear. And chip seal, another example, it's recommended if there is limited cracking, flashing, bleeding, raveling wear, and other methods. And now more about experimental part. So for a thin overlay, we selected crushed quartz diorite with LA coefficient 11, Nordic value 8, and flakiness index 5. All results match Latvian road specification requirements. Here you can see recommendations for S1 class roads. Also, we tested 3 different bitumens, 4580-55, 4580-65, and 4580-80, which are polymer modified bitumen. All results meet Poland specifications, because in Latvia there is no specifications that are in progress for polymer modified bitumen. The next step was designing the mixture. 9 different mixes were designed. A last mixture with bitumen contained 5.5% and aeroids 5.3%. Here you can see asphalt mixture, which we used. Okay. The next step was testing mechanical properties. The thin asphalt layer was formed of the top of the base layer. Base layer thickness 45 millimeters, and thin overlay thickness 25 millimeters. As you can see, results for VTS value was very good, from 0.12 to 0.18. For a base layer, we selected the SMA. Different emulsion were used between a thin overlay and base layer, with modifier and without. Pictures shown cross-section of wheel tracking test sample, and here we can see deformations which are not very deep. So shear resistance between thin overlay and SMA. The best result was obtained by emulsion C65 BP with a 3% modifier. All results obtained meet the requirements for road specifications, which are 8 kilonewtons. Best result 17.9 kilonewton. And now conclusions. So about thin overlays, its advantage is lower costs, good surface texture, noise reduction, improved traffic safety, good performance. Disadvantages may be laid only in good weather. Manual paving is not possible. Aggregate quality must be high. And so you need a high quality magmatic aggregate, polymer modified bitumen with high elastic rejuvenation value, more than 70%. So on performance properties of developed mixes, VTSR 0.12 to 0.18, and shear resistance values exceed road specification requirements for 1.5 to 2.5 times. And the last, not the least, in limited budget conditions, I think we must work on researching other renewable methods to work as efficiently as possible and stick to this sentence to select right treatment for the right road at the right time. And thank you for your attention. And if you have some questions, or if you want to share your experience about the thin overlays, I will be happy to hear it after session.
Thank you, Arturs. If you don't have any questions, then our fourth speaker is Peteris Skels. He's a PhD student researcher at Riga's Technical University, Institute of Building and Reconstruction. He's going to talk about forest road pavement stabilization with wood fly ash. The floor is yours, Peteris.
Thank you. Thank you for a nice introduction. Well, the co-author for this paper is Victoris Haritonis, also Riga Technical University. But for the people involved in this project, not really participated in this paper, but there have been more than 2 people working on this project, which was started in autumn 2015. And second stage of it was finished beginning of this year. So to introduce this project, first why we started it. So there are more than 50 kilotons of wood fly ash generated annually in Latvia as a byproduct. Well, it's of course not comparable to the oil shale ash you produce here in Estonia, but still it's remarkable amounts of byproduct generated, and right now it's just dumped in landfills. Very much overloading them. So on the other hand, forest roads are of course an important part of forest management, and approximately 300 kilometers of forest roads are constructed or rehabilitated annually. And also previous studies in mostly in northern countries like Finland, Sweden, but also Austria, Netherlands, and other places have shown that biofuel fly ashes are suitable for various construction subsectors, including road construction. And of course, there are also technical, environmental, and economical interest to substitute conventional binders if we talk about bound material. So what has been done? Well, as I said, second stage. Generally, this project was divided in two stages, but the third stage is proposed. The third stage is like a pilot project. Well, we're still working on sort of negotiations and discussing this likely possible third stage. But so in the first stage, it was more like a literature study where we discovered previous experiences in terms of technical, economical, environmental aspects, Then we tested also wood fly ash from Folsom, Latvia, is a combustion plant in Jelgava city, which produces or generates approximately 3,000, 4,000 tons annually. And in the second stage of this project, we did laboratory testing, which is the core of this paper. So we decided to mix aggregates. So if you talk about forest road, it's the surface layer, and we use aggregate according to the existing specifications in Latvia for the forest roads, and we mixed them with 10, 20, and 30% of wood fly ash laboratory, and tested for the immediate test to look at the immediate response in CBR test or immediate CBR test. And then we tested also in a confined and compression test after 7 and 28 days hardening. And also, well, the last point, of course, it's more regarding the third stage of this project, is that we were discussing, or we are discussing this alternative in terms of design and construction, or well, possible opportunities and weaknesses for exactly for design and construction. So for the second stage, or even at the first stage of this project, we tested the material from this specific combustion plant. You can see here the chemical composition of the fly ash. This fly ash is not registered in any kind of registry for now, but actually we persuaded them to do it, and right now they are going through the REACH. REACH is the registration of this kind of materials. Maybe some of you might be familiar with this, but anyhow, after some time we will have sort of a certificate for this kind of a material. There is a comparison with typical Portland cement, CEM1. All right, here here you can see the typical forest road structure. We have road surface layer, road base, sub-base layer, and road subgrade. We decided it was partly because, first because on the surface layer we can get specified material which follows the particle, more or less constant or determined particle distribution. And second, that's, it was also in the literature that it is a good idea to work with the surface layer, and its perspective to use fly ash or maybe not only fly ash from biofuel, but other ashes that for this, particularly for this surface layer. So we picked the material from this structure, this surface layer, which is in Latvia's dolomite, fractional dolomite breakstone. You can see the particle distribution we used, and the borders which are according to the specification. And also fractional gravel. So those are two types of materials used in Latvia for forest road surface layer. So we first we started with standard Proctor to determine optimal water content, of course, both for natural or natural, so without any binder. So, and all three different mixtures was 10%, 20%, and 30% of wood fly ash. You can see the shift from left to right and decreasing maximum dry density. It's obvious because first this binder attracts some water, and second, the ash itself is quite light, so the density drops. The same graph for the gravel, but you can see that actually those graphs, the optimal moisture content is, especially for dolomite breakstone, there's no big difference. It's yeah, for the stabilized material is somewhere between 9 and 10. Here is a little slightly greater difference, somewhere between 7 and 9. So we picked those optimal contents, and we tested in, as I said, for the immediate mechanical performance in CBR test, or immediate, so to determine immediate burning is just after the mixing, so to get some properties to see how this material works just after the mixing with binder. So this is what we got. You can see that for fractional dolomite, there is, the highest values was 10%, and then it's dropping. Yeah, it was something similar for the gravel. Anyhow, of course, CBR values are high. Well, this material is not weak soil, it's dolomite, breakstone, and gravel, so we didn't expect that it will be much lower. But in this case, for the gravel, you can see that CBR were actually quite remarkably increased. So, yeah. Then we stored this, so we prepared in proctor molds, 150 millimeters proctor molds, the samples for curing, for hardening 7 and 28 days. And you can see here results for the dolomite after 7 and 28 days. What you can see here is that by hardening in time, this maybe this immediate bearing values are compensated. If you look back here, you can see that the optimal is a 10, but it is compensated by hardening. So actually increasing the amount of wood fly ash as a binder and keeping in time longer, you can see that actually 20 and 30% ahead. It can be seen even more clearly for the gravel that increasing the amount of binder, we actually got higher confined compression strengths, both after 7 and 28 days. Well, we actually also tested with LVDTs attached to the sample. We test also the sort of one-dimensional E modulus. Although in the literature, very often for the design, it's used just confined compression strengths multiplied by some constant values, but we try to determine this modulus by LVDTs. I think we succeed, you can see the values here. That's after, for the gravel, it's even about 400 megapascal. We're still considering how to use those values for the design, but definitely we're not getting weaker material, we get stronger material here. To To conclude this, the main findings from this study, or first two stages of the study, because of in the literature and in a foreign experience, always a pilot project is required to actually to see how this material works in situ. But here in the first two stages, we determined, or we now are sure that this material, this wood fly ash from Fortum Latvia bubbling fluidized bed furnace combustion plant is a good hydraulic binder for the forest road surface layer stabilization. It's both for fractional dolomite, breakstone, and gravel. Even standard proctor test, immediate bearing index test indicated that optimal fresh unbound aggregates mixtures was 10% of wood fly ash. Unconfined compression strength test results show that it is compensated by time hardening for 20 and 30% of this binder mixture. So unconfined compression tests results show that gravel constantly showed increasing UCS values by adding more binder and in time, and maximum values were obtained for 30% of wood fly ash. And you can see here the values we got. And and the final conclusion of finding was that the common practice for design purpose is to take or obtain the modulus from the UCS value. We tried to get it by LVDTs for direct measurements, and here you can see the values we obtained. Here are the acknowledgements. This project was developed in collaboration with Latvian State Forest and Forest in Latvia, and thank you.
Thank you, Peteris. If anybody has a question, then please, short question. Okay, thank you again, Peteris. Very interesting presentation was. Now our last speaker comes from Poland, Mr. Linek Malgorzata. He's a lecturer of Kielce University of Technology of Poland. Okay, lady comes. She is going to talk about pavement quality, cement concrete of extended operational durability. The floor is yours. Mrs. Malgorzata, yeah? That's correct?
Yes,
Okay.
thank you. Ladies and gentlemen, I pleased to present you presentation about pavement quality cement concrete of extended operational durability. Concrete airfield as a special type of construction which is exposed for the load supplies caused by movement of aeroplanes, natural load caused by change of temperature in the cycles of day and night, and the forced thermal loads caused by hot exhaust gases intended for the airfield pavements from the nozzles of the aeroplanes engines. Durability of the airport pavements is intended with the ability of pavements to carry loads in established period of use. Today I would like to say about two composition of the concrete mixture. The first is the standard composition intended for the concrete airfields and according to the Polish standards. And the second is the optimal composition of the component which have the modified composition. The requirements of the airfield pavements and parameters which these airfield pavements should be resistant to be environmental impact. This impact was included such as frost corrosion, corrosion caused by carbonization, corrosion caused by chlorates, and absorption impact. It is recommended to use Portland cement of clinker type, which minimum class is 33.5, and very important is the cement concrete intended for pavement should be a low alkali type, so the content of the alkali more than 0.6% alkali. Cement content in concrete mix is diversified and closely dependent on the parameters of the designed concrete. Here we can see the requirements for the concrete pavements. In the table 1 we can see the parameters which was dependent on the environmental impact, and concrete mix included water. In the amount depended on the assumptant of water-cement ratio. This ratio is different. For Polish standards was from 0.45 from 0.45, 50 from dependent on the environmental impact. For the airport pavements, the maximum volume was included 0.4. The use of the water should be have any not be any smalls, should be value more than 4, and other parameters which we can see. The most significant component of the concrete mix is aggregate. Aggregate content in the mix is from 70 to 75%. The type of the used aggregate is of primary importance in the shaping parameters of the hardened concrete. The aggregate used in case of airfield pavements should comply with the requirements included in the table 2. And here we can see the two types of the aggregate. Coarse aggregate, which the fraction of the grain was more than 2 millimeters, and fine aggregate when the aggregate from fraction below the 2 millimeters. Here we can see the parameters of the physical and mechanical parameters for airfield pavements for the aggregates intended for the airfield pavements. Grain size distribution curves of the designed mixes should be between in the limit curves. Figure 1 and Figure 1 and Figure 2 presented the good grain size for the aggregate. This area gray, this is the area which indicate the range of the good grain size distribution. One of the methods of ensuring the reliability and durability of the cement concrete intended for the airfield pavements is a technological solution. And today I would like to say about concrete, cement concrete, class C C4050, intended for airfield pavements and requirements from Polish standards. The parameters and materials which was used to the components of the concrete CC1 for the standards components and CC2 was presented in the table. There were analyzed two sets of cement concrete CC1 and CC2. Material composition mixture were presented in the table, and in the composition of CC2 concrete concluded why one materials others in the concrete one. That's a modifier. This modifier is the ceramic additive, which have very high performance for the change of temperature. And replacement the fine aggregate on amount 10.5%. The study included three research series A, B, and C. In the series were different parameters, the influence of the applied dust on the change of register blending, strength of concrete with respect to curing time was determined. In series B, the blending strength with respect to the curing temperature, and in series C, influence of the applied ceramic of the dust absorbability and frost resistance were determined. Research periods which was included in this test are presented in the table 4, and characteristic of the research in series A included 4 curing period. The first period included from 1 to 28 days, and here curing condition was standard, so the temperature of the curing was 20 Celsius degree. In step 2, the curing period from 29 to 56 days of curing. The sample was prepared in the laboratory conditions. Here temperature was about 22 Celsius degree and humidity from 45 to 65%. In the step 3, from 57 to 1 year, the sample was curing in the real condition. Average temperature was 10 degrees Celsius and average rainfall about 580 millimeters. In the first step, from 1 year to 5 years, the sample of the concrete CC1 and CC2 was curing in the real condition, and here average temperature was about 8.5% and average rainfall 640 millimeters. The influence of the series C was included 3 different temperature curing. The first step included decreased temperature, and here the sample was prepared in the temperature from 20 to 60 degrees Celsius. The second step included increased temperature from minus 20 degrees Celsius to 20 Celsius degree, and the third step of the research include variable temperature. Single research cycle included the heating and cooling. Process of the heating was prepared in the temperature 250 Celsius degree, used from the nozzles as used in the aeroplanes in the Poland. And this time of the of the one cycles for 60 seconds. And the second period include the samples were cooled in temperature 20 degrees Celsius for 90-100 seconds. In the series C was determined the absorbability, which was intended for the airfield pavements with Polish standard no more than 4%, and the frost resistance. This research included assumpted number of 200 freezing and defrosting cycles in two other agents, water and carbonate. In order to assess the impact of the used ceramic dust on the change internal structure, concretes of series A, B, and C were subjected to observation in scanning electron microscopy. According to the analysis of the obtainment test results of concrete series A, it was proved that mechanical parameters of concrete CC2, that's here, in all analyzed cases are higher than parameters of concrete CC1. The reason of increasing the durability of concrete of series CC2 is the influence of the used dust on the variable change in internal structure of concrete composition. Figure 6 presented the internal structure of cement concrete series CC1, and here we can see the micro cracks in the air pores in the contact zone between cement matrix and grain aggregate, and from the cement matrix on the cement matrix we can see the crystallization of the ettringite, which the width of these crystals more than 10 micrometers. Figure 5 presented the microstructure of the cement concrete CC2, and here we can see we cannot see the micro cracks. This layer is continuously on the in the cement matrix. We can see the crystallization other than in concrete CC1, and this crystals of ettringite is not here. According to the analysis of the obtained results of concrete CC1 and CC2 in series B, it was proved the concrete of series CC2 responded to the change of curing conditions to the lesser degree. Here we can see the parameters of the concrete CC2, and here we can see the parameters of the concrete CC1 in other temperature after research in concrete B. Significant impact of the applied dust on the bending strength of concrete curing in various environmental conditions was proved. And here we can see, according to the analysis, the obtained test results, concrete C, it was proved that CC2 concrete is defined by lower absorbability. In figure 8, we can see the more absorbability for the concrete CC1, and here we can see the less absorbability for concrete CC2. Figure 9 presented the internal structure with porosity. Very important is that for the concrete, cement concrete intended for the airfield pavements, this distance between the buoys and and the size of the air content was the less. And here we can see the internal structure with small polars, and the distance between is less without the concrete one. The analysis obtained test results concerning Series C provide the increased strength of concrete of CC2 series during the frost resistance test. On the figure 9, we can see the structure with porosity of cement concrete A and B. And here we can see the more micro cracks and intensity of carbonization crystals of the attringite for the concrete CC1 after freezing and defrosting cycles. And here we can see the structure of concrete CC2 after defrosting and freezing cycles. After research was obtained, be concluded the significant influence of the use dust on the change of parameters of cement concrete intended for airfield pavements was proved. Dust additive influence the favorable change in concrete microstructure, change of distributed components and their ratio. It was proved that concrete with dust additive is designed by better development, porosity structure in case of CC2 concrete. There are more eye voice, the diameters of which do not extend 300 micrometers, and more favorable porosity quality in the concrete structure containing dust influence, the reduction of concrete absorbability and increasing frost resistance thereof. High durability and resistance of dust to temperature variations contributed to the increased thermal resistance of concrete. And thank you for your attention.
Thank you.